Hello everyone, today's lesson is solving logarithmic equations. In logarithmic equations, we're going to see one or more terms expressed in logarithmic form. And since we're solving equations, a lot of simplifying will take place, which means that we need to combine the logarithmic terms very often. In order to combine logarithmic terms, on the other hand, we need to use the logarithmic properties and logarithmic laws. So before we start, let's quickly review the logarithmic properties and write them down here so we have them handy as we go over the examples. So the first logarithmic property is that, or states that the log with base a of number 1 equals 0. The log with base a of a equals 1. The log with base a of a to the power of b equals b. And a to the power of log with base a of b equals b. So all these are what we call the logarithmic properties. Okay, and the next formula that will come in very handy when we solve log equations actually is what we call the change of base formula. The change of base formula states that if we have a log term expressed in the form log AB, then we can rewrite this as log of B divided by log of A, provided that we assign the same base to both log terms. So again, this is the change of base formula. And next we moved on to logarithmic laws. We had 3 of them, just like exponent laws. Number 1, the product law, which states that the log with base a of xy equals log with base a of x plus log with base a of y. Next, log with base a of x over y, we are into quotient law now, is log with base a of x minus log with base a of y. And last but not least, log with base a of x to the power of r equals r log with base a of x. So that's a power law. So these are the 3 laws. Now remember that the product means you add the logs or add the exponents. For the ratio of exponential numbers, you subtract the exponents. And for the power, we bring the power here into the coefficient. So I'm going to box them up. And these are the laws. Okay, let's go over a few examples. So example number 1. What we see in this example is that we have log with base 3 of 9, log with base 3 of x, and log with equals log with base 3 of 24. So 2 things we need to keep in mind when we solve log equations. We want the bases in each and every log term to be the same. Why? Otherwise, we won't be able to combine them if they don't have the same basis, just like with exponential numbers. Number 2 thing is locate where the unknown variable is. In this case, is going right here in this term. Just like in linear equations, what we can do in here is isolate the term that contains the variable, or simply combine these 2 terms. So 2 different strategies. I'm going to go with combining the log terms on the left side first. So since we have a plus in between, that means that we are adding the exponents, which means product law. So we're going to write log with base 3 of 9x equals log with base 3 of 24. And from here, we're going to compare left and right side when we arrive at the point that we have 1 log term in each side. And we're going to think, okay, 2 logs that are equal, they have the same basis. That makes the expressions inside them be equal. So therefore, we're going to say x equals 24 over 9. Or even better, x equals divide by 3, reduce by 3, 8 over 3. So this would be the solution. Very often we need to, actually not often, but you have to always check and see whether or not the solution is valid. Remember that x is inside the log in here, and we know that here we only need to have positive numbers. So another method or another way of solving this equation would be, here I'm going to separate them a little bit here, would be by, let's make it perfect, so will be by actually isolating log with base 3 of x. So we're going to say that log with base 3 of x equals log with base 3 of 24 minus log with base 3 of 9. That will make log with base 3 of x equal to, so this time, notice that we have a minus, which means we are using the quotient law, and then we'll write log with base 3 of 24 over 9. So that makes x equal to 24 over 9, or 8 over 3. And that's what we found out using the previous method. Okay. Alright, so we'll move on to the next example. Example 2. In example number 2, we have log 7x squared equals log 716. Remember we said that we need to look at two things, so the bases are equal. So we have a single log in each side, so we don't need to do any combining of the log terms. So we can jump ahead and write down that x squared equals 16. So x then must be equal to plus or minus 4. You got to be very careful with the positive negative solutions, because when you have x terms inside the log, we need to double check and see whether or not they will produce any negative numbers. The numbers inside the log must always be positive. So we'll have x equals 4. And if that happens, log with base 7 of x squared will be log of 4 squared. So that actually will give a positive number, and we're good with that. So we're going to give this answer a yes. And if x equals negative 4, then log with base 7 of x squared would be negative 4 squared, and this is also a positive number. So we'll give a yes to both answers in our case. So x can be 4 or negative 4. Okay, so in the next example, we have log 2x minus log 148 equals 2. So the things that we see that are different, a little different than the previous examples are, number one, we don't see the bases in the log terms. So when we don't see the bases, it means that the base must be 10. Remember that we mentioned that base of 10 not necessarily necessary to write. Another thing that gets my attention here is the fact that here we have a log and then another log, but here we have a number. When this happens, meaning when we have a combination of log and normal numbers or normal terms in a log equation, then what we do is we combine all the log terms together and we leave the numbers or the normal terms in the other side on one side of the equation, so together. So in this case, we're going to say that we need to apply the quotient law in order to combine these two terms. So we'll write log with base 10 of 2x minus log with base 10 of 148 equals log of 2x over 148. The base is 10. And that would equal 2. If you'd like to, you can simplify it a little bit more. Why not? So that's x over 74. The base still 10. Okay, equals 2. So at this point, in order to solve for x, we're simply going to use the definition of log. Or in other words, we will convert this log expression into an exponential expression. So according to the log definition, then we're going to say that this base of 10 raised to the power of 2 must equal this exponential number, right? So we're going to write 10 x over 74, better leave x in the left side, equals 10 squared. So that will make x equal to 7,400. And that would be the answer to this equation. So in the next questions, actually, notice that I wrote here practice. That means that I believe that you have enough skills to be able to solve these equations on your own. So if you would like to, you can pause the video and practice on your own. If not, then I'll continue solving them. So I'll follow the video. So log with base 2 30x minus log with base 2 5 equals log with base 2 12. I'm happy the bases are all 2 and I only have log terms. I can combine them in different ways. And I am choosing to keep the log 30x in the left side. Bring this to the other side because I like the product law better than the quotient law, but it shouldn't make a difference. So I'll rewrite it as log with base 2 of 30x equals log 212 plus log 25. I'll simplify. You know how it is. Just like in any equation, we move terms around or simplify, move again, simplify, right? So log with base 2 of 12 times 5, which is 60. So again, as we've mentioned, so we have same basis, equal logs. So we're going to say that 30x must equal 60. That will make x equal to 60 divided by 3, or x equals 20. Okay, so moving on to the next example. It's got to be straight. So log x minus log x squared equals 12. So we have the x terms in one side. We'll keep them in the left side of the equation. Why not? It doesn't really hurt to take them to the other side as well, but it makes the process a bit shorter, I think, if we kept them on the left side, on one side together. So we have log of x divided by x squared equals 12. The base, I don't see it, which means that it must be 10. And from here, we're going to say that x over x squared equals 10 to the power of 12. I can reduce this to 1 over x, and whenever I do such thing, I make sure that I write the restriction x is different than 0, just in case we end up with a solution of 0. So if 1 over x equals 10 to the 12th, obviously leave this in exponential form, then that means that x must equal 10 to the negative 12. Okay, so 10 to the negative 12, remember, is a positive number, or we can write it in this form as well, right? So it's a positive number. So do not be afraid of plugging in x into plugging in x in the equation here, in the log terms, okay? So it's a positive, so we're good. Okay, so next example is log with base 2 of x plus 3 plus log with base 2 of x minus 3 equals 4. So what we have in here is 2 log terms and 1 constant. When this happens, I want all the logs in one side, constants in the other. So log with base 2 of x plus 3 times x minus 3 equals 4. So log with base 2 of x squared minus 9 equals 4. So we have to follow the same strategy we did in example 3. Was it? Yeah. And we're going to to say that x squared minus 9 equals base 2 to the power or to the log 4. So x squared equals 2 to the 4 is 16 plus 9. That will make x equal to plus or minus 5. So now let's think about our solutions. We got two of them, x equals 5 and negative 5. So if x equals 5, then log with base 2 of 5 plus 3 exists. So we're going to give this a yes because that's a positive number. Now if x equals negative 5, then log with base 2 of negative 5 plus 3 doesn't exist because that's a negative. So we have to test the x equals 5 in x minus 3 as well. So log with base 2 of 5 minus 3 also exists. So we're going to say that this one is negative. X equals 5 we had no problems with, right here. And this x equals 5, no problem with that. So we'll accept them. But x equals negative 5 didn't work out for us. So we're going to give this a no and we'll reject it. So the next example is log of 5x minus 1 minus log of x minus 3 equals 2. So again we have minus, quotient law. Similar example to question C. So we go log of 5x minus 1 divided by x minus 3. We don't see a base, that means the base is 10, and that equals 2. So 5x minus 1 over x minus 3 equals 10 to the power of 2. So 5x minus 1 over x minus 3 equals 100 over 1. Or 5x minus 1 equals x minus 3 times 100. 5x minus 100x equals negative 300 plus 1. Negative 95x equals negative 299. X equals negative 299 divided by negative 95. And even better, we're going to say x equals 299 over 95. Okay, so that would be the solution here. All right, moving on to our last question, practice question. We have, let me do this a little better. Okay. All right, so the next example or next question is log 9x minus 5 minus log 9x plus 3 equals 1. So we have a similar situation as in the last two questions, and we are going to combine the two log terms, leave the constant in the other. So log with base 9 of x minus 5, x plus 3 divided by x plus 3 equals 1. So x minus 5 over x plus 3 equals 9 to the power of 1. X minus 5 over x plus 3 equals 9 over 1. So x minus 5 equals 9x plus 3. So take 9x to the other side, negative 8x. Take positive 5 to the other side. I mean negative 5 becoming positive 5, right? So x equals negative 4. Now we're going to check and see, all right, how is this going to work for our equation? if x equals -4, then we will have log with base 9 of -4 minus 5. Now this will be a negative number. A less than 0 number doesn't exist. So we're going to say we are unhappy with x equals -4, and we'll reject this solution. Okay? So we have no solution for this equation. All right? So